Fats and oils, commonly known as lipids, properly known I should say as lipids. Lipids is the broader class, containing other things as well, such as waxes and steroids. Now, fats and oils, commonly used terms, it's basically a functional distinction. Fats are solid at room temperature, oils are liquid at room temperature. So generally the ones that we look at chemically are known as triglycerides. They are esters formed when an alcohol, glycerol, 3 carbons, 3 hydroxyl groups, reacts with 3 long-chain carboxylic acids, 3 fatty acid molecules. Now you've always got lots and lots of long hydrocarbon chains, so these are highly non-polar molecules. You've got a few polar bonds, polar groups hidden away in the ester functional groups, but overall the effect of the long hydrocarbon chains is much more powerful. These are highly non-polar. So let's look at the reaction. It's the ester reaction, of course, which hopefully you're all familiar with now. So we've got our glycerol. So our alcohol with 3 carbons, each carbon's got an OH. In your data book, if you can't remember, you've got 3 fatty acids. So here I've given a fairly simple one with 15 carbons, not sure which one that is. Then we're not too concerned about that. All we're interested in really is the functional groups reacting. So it's the ester reaction. So we lose the OH and the H. That produces water. And then we join what's left over to get ourselves an ester bond. That occurs 3 times to produce our triglyceride. It's the ester reaction. So the forward reaction is a condensation reaction. The reverse reaction is a hydrolysis reaction. So when we eat fats and oils, in our gut we break down our triglycerides into fatty acids so that they can be absorbed into the body. Types of fats, we categorise them on the basis of the carbon-to-carbon double bonds. So, saturated fatty acids have got no carbon-to-carbon double bonds in them. Stearic acid is a common one of those, and because single bonds are much more flexible than double bonds, these molecules can pack more tightly together. They can fit close together when they're tight packed. Getting close together means stronger dispersion forces, means a higher melting point. So they stay solid at room temperature. So animal fats tend to contain more saturated fatty acids, and various impacts on lipid metabolism. If we look at the formula, we would see that it has got a degree of unsaturation of 1. Chop off the 2 oxygens, you end up with a molecular formula for this one of C18H36, and 32 is 35, 36, so C18H36. Of course, the alkane would be C18H38, so it's a degree of unsaturation of 1, and that is due to the C double bond O in the carboxyl group on the end. So there's always that extra degree of unsaturation in a fatty acid due to the carboxyl group. We're not particularly interested in that, we're interested in the carbon-to-carbon double bonds, and this one has got none of them. Mono unsaturated, mono 1 carbon-to-carbon double bond. Oleic acid is an example of that, given semi-structurally here. And what that does is it puts a kink in the chain. Degree of unsaturation of 2, so the carboxyl center bond O plus 1 carbon-to-carbon double bond. Polyunsaturated, many carbon-to-carbon double bonds, and linolenic acid contains 1, 2, 3 by the look of it. And that puts 3 kinks into the chain, so it has that rigid structure, stops it packing close together, which decreases its melting point and is much more likely to be a liquid at room temperature. Also, those carbon-to-carbon double bonds are reactive, which means the addition reactions can be undergone and they'll break down more quickly. And this one would have a degree of unsaturation of 4 because of those 3 carbon-to-carbon double bonds. Now, omega numbers are not in the course for this year. I've kept the slides in because it's kind of interesting to know where those terms come from, but you don't need to know this for the exam. Omega-3 and omega-6 fatty acids. Basically, how far the double bond is from the back end of the molecule. Now, the alpha carbon is at the front of the molecule, close to the primary functional group. The omega carbon, omega is the last letter of the Greek alphabet, so that is the molecule at the end of the fatty acid chain. So we count the number of carbons till we get to the double bond. So this one is omega-3 because the double bond starts 3 carbons in from the end of the chain. So it's the first one we get to, which is how we classify the amino acid, sorry, the fatty acid, and this one's got 3, so it's omega-3, 4, 5, 6, 7, 8, 9, so omega-3, 6, 9. The first double bond starts 6 carbons in on this fatty acid, so that is an omega-6 fatty acid. High melting point caused by stronger dispersion forces because, well, a few things can cause that. If you've got a longer chain, you're going to have stronger dispersion forces, simply the molar mass effect. So 2 saturated fatty acids there, lauric acid, stearic acid. Stearic acid is 6 carbons longer, therefore melts at a much higher temperature. Fewer double bonds means closer packing. Molecules can pack more tightly, stronger dispersion forces, higher melting point. So compare 2 fatty acids with 18 carbons, stearic and linolenic. Stearic is saturated, linolenic has 3 carbon-to-carbon double bonds. Stearic acid is a solid up to 70 degrees. Linolenic acid turns into a liquid at -11. Have a go at those questions and I'll give you the answers when you submit them.